Welcome, everyone. Thanks for joining us and thanks for being part of our community. My name is Valan Kolika and I'll be your host for today. Just a few reminders before we kick off this webinar. If at any time you experience issues viewing the stream and are using the web browser version of Teams, please refresh your browser. If you're using the desktop app of Teams, please exit and rejoin. This seems to resolve the connection issues sometimes experienced with our native hosting platform here. Please note that this webinar is being recorded and will be shared publicly. We will post the recordings on our community at aka.ms/security-webinars. Closed captions in several languages are available during the live broadcast, and you can enable them by clicking on the CC button located at the lower right corner of your screen. Feel free to ask questions at any time by typing them in the live event Q&A window, simply by clicking on the Ask a Question button. Be aware that any questions you post will be publicly visible. However, if you prefer, you can post your question anonymously by checking the box right below where you enter it. Now, we love to hear your feedback on how we can improve on these webinars, and you can do so at aka.ms/security-webinar feedback. And by the way, all the links that I'm announcing have been already shared with you on the chat. And I would also like to invite you to join our public community by visiting aka.ms/security-community. That's the best way to ensure you don't miss any future webinars or major announcements. On our community, you can speak directly to our engineering teams that create our security products. You'll be able to influence our product designs and get early access to changes by doing things like participating in private previews, which, by the way, you can sign up for at aka.ms/security-prp. In there, you can request features, give feedback, review our product roadmaps, register for events, or just simply join webinars like this. We believe that the best way to improve our products is by removing any barriers between you and the people that create them. So we hope you'll join us. In today's session, Michael Hendrickx will go over the best practices of authentication and authorization methods. Michael is a senior security engineer manager with the Microsoft security team, and without further ado, I'll turn it over to him. Michael, the floor is yours.
Thank you, Valon. Good morning, everybody. My name is Michael Hendrickx. As said, I am a senior security engineering manager in the Azure security team. And we're going to talk a little bit about authentication and authorization today, especially what are the best practices to do this well when we're writing code, when we're creating our own libraries and our own products. So basically, identity and authentication is sort of at the cornerstone of security. You need to identify to a system in order to sort of get roles granted to you and whether you can do something or not. So seeing that authentication and authorization is really important, I want to simplify it down to sort of three major rules. Don't talk to strangers. Do the right things when you're getting or minting your initial bootstrap secrets. And when we deal with more secrets, which is in the end how we identify ourselves, how do we store or handle these securely? So diving straight into it, don't talk to strangers, or basically from a computing point of view, this means is the endpoint really who it claims to be? For example, one of the common scenarios what we often see is the so-called evil coffee shop scenario. The network that you connect to might not always give you what you expect it to be. In the last year, we all know that remote work has increased quite a bit, and that has increased the risk of Wi-Fi attacks as well. Not just on those so-called evil coffee shops, but also just on your home network. Suddenly, if you're working from home, your home network becomes an extension of the corporate network, and whatever you do there sort of extends into the general security posture. So, for example, if you are on a network, on a Wi-Fi network, and you would try to go to Azure.com, the real DNS server might actually say its IP address 13.94 or whatnot. This will expire in 5 minutes, so it makes sure that for scaling, we can fail over to different IP addresses. Now, this all depends on the wireless network that you're on. In fact, if you're on an evil network, the DNS traffic could just be man in the middle, as they call it, and a response could be given back, which is the wrong one. So from that point of view, DNS resolving could be dangerous. We have this, within security, we call it a TOC2 issue. It's a time of check versus time of use. There's a certain challenge when we check whether a host name has a certain IP address, and when we actually use it, it might have been changed. And that's sort of what DNS rebinding attacks are. And other than a more modern DNS over HTTPS or DNSSEC, not all DNS traffic is secure. It was initially created to route packets over the internet to change host names to IP addresses. So it was initially created just to facilitate functionality, not really security. And one of the problems what we have in cloud providers, and Azure has this problem on a few of its resources as well. You have something called dangling DNS domains. For example, the example you see there at the bottom, myservice.contoso.com would be a vanity domain. It's my domain name. I own contoso.com, and I would forward this to any VM, any cloudapp.net machine. If I remove the machine and I no longer use it, that DNS, they call it a CNAME record or a CNAME forwarder, is still in DNS. So unless you remove that as well, an attacker could register the same VM name and suddenly has a host name with the valid domain name pointing to it. This turns into a little bit of a bigger problem if you have certificate authorities that will give you a certificate based on your domain name, but that's a completely different story there. Also, one thing to hold up or to keep in mind there as well, when we use DNS names, remember that these can expire at some point. So if we have them somewhere in a configuration file and a domain expired, anyone can pick up these domains and sort of see what traffic goes to these things. For that, we'll dive into our first spot a security bug issue. This makes a little bit more sense in an interactive environment. Now I know there's a little bit of delay between the chat and what I'm saying. So unless you can yell loud enough that I can hear it in Redmond, I'll go ahead and I'll sort of talk to what the problem is here. This is actually some source code we found quite a while ago in one of our source code repositories, and we noticed that there's a security bug here. And my question would basically be, how can an attacker attack this? What sort of payload would slip under the radar for these things? And the answer for that is relatively simple. Someone who owns a domain name, say attacker.net, could just put a prefix to it. If you own the domain name, you somehow own all the subdomains there as well, and you can add you can just add a prefix to it. To fix it, or actually these are three different security bugs in there. If you look at the original line, we check the absolute URI, which is the entire URL. So technically an attacker could just take its own domain, attacker.net, and put anywhere in that URL, a string or something, visualstudio.com, and that check would have passed. And one thing further to that as well, and why that dot in front of Visual Studio is important in the green line where we fix it. If you don't do that, anyone could create abcvisualstudio.com as one domain name and still be able to bypass the attack as well. This is hard to find during normal static analysis. These aren't illegal functions or banned functions which we're using, but these are bugs that have disastrous problems in the entire authentication authorization space. So DNS is not always a safe thing. But then people would say, if DNS is so bad, what do we do to protect it? What's the silver bullet? That silver bullet comes in the name of TLS. It's transport layer security. You may have heard about it as SSL before as well. If you, and most of us are, but if you're hosting a web app or a web API, if you need to reach a web app or web API, it's extremely easy. You need to enable HTTPS on the endpoint, and most of the client libraries will have transparent HTTP and HTTPS capabilities. It's important to do this at the very first request. Any request that happens in clear time between a client and a server can be intercepted and can be changed. even if the reply and one of the HTTP headers would do that, saying all the follow-up requests, make sure they're encrypted, that very first request can always be rewritten, and any security headers in there can be left out. So for HTTP, that's easy. If you're not using HTTP or HTTP, if you don't have a web app or a web API, and if you have a more custom protocol, try to wrap it in TLS. There are multiple libraries out there. It will give you strong authentication as well as integrity as well. Whatever you do, try to not roll your own cryptography. When 9 out of 10 times when we see within Azure, when people try to do something themselves, when they try to recreate what TLS actually gives you, for example, we do see architectural flaws or implementation flaws. That's partially because TLS is not just about confidentiality. We don't take a data stream and encrypt it, but it's also about data integrity. And we'll talk about that in a second. When using TLS, it's really important to not use old versions. A lot of people would enable TLS on their machine or on their web server and think that they're secure. But the older versions, SSL v3 and versions like TLS 1.0 and 1.1 have security vulnerabilities in there where people could downgrade the encryption and read or manipulate the packets in between. And obviously with all certificates, what you get, you need to make sure that you verify or that you validate them. So as I mentioned earlier, when you have that TLS is not only about encryption, it's also about data integrity. It can actually give you authentication as well. If you just want to use the same protocol, the client will authenticate the server. That sort of gives you the confidentiality. The server will give you the public client, the public key that only it can decrypt with its private key. But optionally, as a client, we can also give our public key. So the server would know that it's really us that they're talking to. Cryptographically, be very sure about this. When we do pass on a certificate, either from a client to a server, or when we ingest on a certificate from the server when we are the client, we always need to verify it. In .NET, the standard verify call does not check for revocation. So that may be something that you might want to do explicitly. And the authorization is typically done by certificate pinning or something we call SNI, which is the subject name and the issuer. With certificate pinning, and that's the only time we allow self-signed certs, you would basically say this certificate with this thumbprint or with this public key is allowed. And so far, we've never seen two different certificates with the same thumbprint on the internet. Or we can say we only allow certificates that are issued by this issuer, but has this particular subject name. And then we sort of want to make sure that there's some trust in there, that issuer, that certificate authority, would not just give certificates to everybody in the world. How to not do TLS certificate validation. This is a snippet I wanted to bring on. This is something we find in pen tests in Azure every now and then, where we quickly, when we're testing a service, are using self-signed certificates or aren't using the production certificates yet. And somehow someone would quickly bypass any checking and we'll fix it later when we go live. These are things we look for specifically, because this would mean that any certificate, whether they're self-signed or a very valid one, would actually work. And this would reduce your authentication to, if you have a certificate, you're authenticated, which causes a lot of problems. This is how to do it in .NET. In Node.js, which is a language we see coming up a lot more as well. In Node.js, we need to ensure that TLS checks aren't disabled. For example, by default, a environment variable could disable your Node.js process to validate certificates properly. You can also do it by setting the reject authorized attribute to false, and when we create an external HTTP request. When we look for this in the public GitHub repos, we still see these things being happening where someone explicitly disables security. And I didn't wanted to call out the developer itself there, DVD Knapp, but I wanted to highlight that we often have these things set up in, we often have these settings set up in example configuration files. And a lot of people, to create a configuration file, would copy the sample, cut out whatever they don't need, and sometimes leave these things in there, put their real value in there, the host names and whatnot, and then suddenly you're running an insecure service. So for that, TLS is very important. With that, we know that we're talking to the right host name. When we get a certificate, we can cryptographically be sure that we're talking about the right thing. So then we can say, so we validated the hosts now. Is this good enough? Endpoints are usually the host name we talk to, portal.azure.com. We don't always consider the entire URL. One of the bugs we found quite a while ago in Azure was that there was an authorization bypass when we were just looking at the URLs. And what this basically means is you had a web request that would go through an authorization layer, and then afterwards through a business layer, a logic layer. In the authorization layer, we would look at a value as a string. The entire URL would just be a string. You can see there that we have a certain subscription that we would pull out of the string, and we would do our authorization security decisions against that. Now, once the authorization was successful, we passed it on to the logic layer, who would take that string, make it back into a URL, normalize it, and then work off those resources. Now, normalizing a URL by most libraries will put any dot slashes back to the parent directory and would overwrite something. So by sending a specially crafted URL, we were able to bypass the authorization layer and talk to the wrong subscription from a logic layer point of view. Again, very hard to find within static analysis, and this is something where pen testing and security reviews come in very handy. So now we talked a lot about talking to the right endpoints. The next thing we're going to talk about a little bit is getting and minting our secrets. Where do we find our first secret to sort of get in the door, or get an identity so we can download our other connection strings and our other secrets? And that's relatively complicated, or there's a lot of questions we need to keep in mind there. When your program is interactive, we should try to challenge the user. Of course, being a security person, I hope that everybody on the call have MFA enabled. If not, you should do it soon, and you should tell your friends and family to enable MFA as well. It just creates a lot more personal security in your accounts. If it's not interactive, or one thing I quickly want to talk about interactive as well. If you know that a program is going to be largely a single user program, you might be compelled to hard code or make it a lot easier getting this identity. Every time you make that assumption from a security point of view, you should always think that what would happen if someone else would run this program if you don't know whether the user that's running the program is actually the real user. So that's something to keep in mind. If it's not interactive, if this is a web job or a cron job that's running every now and then, one of the best things you can do within Azure is using something called a managed identity. A managed identity basically would connect to an endpoint that only makes sense to your Azure resource. It's a non-routable endpoint. It will get an identity from Azure Active Directory, and with that, it will get a valid signed token. With that, you can give access to key vaults or storage accounts to download additional data. If we can't use a managed identity, you should opt for client certificates. It's easier to revoke them. It's easier to have more metadata around them as well, or towards symmetric secrets. The downside with symmetric secrets, I will talk about them in a second as well, is that you need a secure way to distribute them to an untrusted party, or to a trusted party over an untrusted medium such as the internet. One thing you should never ever hard code your secret in source code. Someone will find it, someone will abuse it, and it's bad having secrets in there, and it's just a very big hassle as well, which we'll talk about in a second. Talking about bootstrapping, that very first secret, what we need to start something is made a lot easier by something called Azure Identity. It used to be a library called App Authentication created by the Green team, and it got adopted by the Azure Identity library. Basically, what this allows you to do is, especially in a dev environment, if you're using Visual Studio or VS Code, it will automatically take the profile that you're logged in with there. If you're running Azure PowerShell or the Azure CLI, the command line interface, it'll take the credentials from there, just with the same snippet of source code. When you deploy this into production, it will see if you have particular environment variables or if you have the managed identity enabled. So there's a lot of different ways to automatically get an identity and be authenticated without ever having to hard code any secrets in there. In fact, the snippet of codes in there is basically all it needs. In the end, the variable secret will be a connection string that just by looking at the source code, you may know where it is. It's in a key vault somewhere. It doesn't mean that you have access to it. But when I run it, it'll take my credentials. When this code runs on my VM or in my app service, it will take the credentials of that machine and they'll all have access to key vault, which makes it very easy getting secrets out of source code. To stress it again, never ever put secrets in your source code completely. If you did, remove it and rotate it. Some people remove the secret, don't really rotate it because it's a hassle. You need to change all the database servers passwords, or you need to tell all these clients or roll any certificates and whatnot. I know it's a hassle, but if you don't, there are a lot of tooling, a lot of hacking programs out there, a lot of tooling from the security community. Trufflehawk, I think, is one of the more famous ones. It searches through your repository for secrets. It does sort of pattern matching there, but it also goes through your Git history. So even if someone said, hey, you forgot a password in there or a symmetric key or an API key, please remove it. And you remove it, check in your new source code, and you think you're safe. Trufflehawk will still get the old secret. Or will still get the valid secret from your Git history. So whenever secret is exposed, consider it compromised and rotate it. The moment you have to rotate a secret once or twice, you'll realize that saving some time by putting them in source code is not a great use of time in the long run. Some teams come to us and they say, hey, we're not storing secrets. We actually store our password in Key Vault, but we store our other secrets right here and they're encrypted. So you still need to go to Key Vault, get a symmetric key or get a password, and decrypt the secrets we have in our configuration file. Is that allowed? And our answer on that is simple. It's not allowed. And that purely means that's purely made possible because an attacker can crack your secret offline and can do this very fast. They can download your configuration file, run this against very heavy, or run this on VMs with very heavy GPUs and CPUs, and they'll be able to crack your secret. The moment they have your key that's used to encrypt all the other data, it's basically game over. They have all your secrets. If you do this as well, you actually have quite some overhead for rotating keys. All the keys that you store encrypted, you need to rotate them as per your policy and the password that you use to encrypt them with as well, which basically means that if you're storing 100 secrets, you need to, every X amount of days or every X amount of weeks, you need to decrypt all of those with the old key, generate a new key and re-encrypt them and hope that everything worked well. So a lot of overhead, and it doesn't really buy you a lot of security. One of the things about cracking offline as well, it's something that you don't notice. No one has to send 1 million or 1 billion passwords on your API because you can detect that and block IP addresses. If this happens offline, you don't know what happened. The next time you're gonna hear from the attacker. So when they actually have a valid identity there. And as I said earlier as well, leverage a platform such as managed identities. Yeah. Moving a little bit towards creating secrets. So we heard a lot about where to get them from and how to do those things correctly. When we generate one, at some point we might have to generate a password, or we might have to generate an API key or certificate. We need to keep a few things in mind. One, do we trust the party that's creating the secret or that are sharing the secret? As I mentioned earlier, when you have a symmetric key, you need a trusted channel where Alice and Bob can say, here's the secret password. They need a trusted channel to send it over. And that's sort of where TLS or public key infrastructure comes into play. Second thing where we should look at is the scope. Do you need to encrypt something? Do you need confidentiality, or do you just need authenticity? We often see in threat models that people say we have this file, it's only for this one person, so we're going to encrypt it with a key. We're going to share the key out of band with the other party, and they're going to decrypt it so they know it comes from us. In this case, what you need is not really encryption. What you actually need is digital signatures, is authenticity. You need to validate that the data came from party that you trusted. It doesn't necessarily mean that it's secret data. Another thing to keep in mind, and this is actually a biggie, is does a human need to know and remember the secret? Computers are good in storing a 1000-bit key. As users, we are not so good at remembering 128 characters. So those things keep in mind, because if you make your security too hard, especially for humans to remember, they'll either, if you're lucky, use a password manager. If you're not so lucky, they'll write them down on a post-it note. And obviously, especially if you're developing things in the IoT or the embedded space, are there any hardware constraints in there where you might not have TPM on the chip, or you might not have a lot of battery or a lot of CPU power to generate a lot of private public key pairs. Last thing to think about is how long does the secret need to live? Most companies have password policies that say change your password every 70 days, and you can't use the last 12 passwords what you used as well. This is the same with machines as well. Symmetric keys, you have to rotate them every now and then. The fact that if it got compromised, you might not always know about it. By rotating keys, you take that question, or you take that ambiguity out of the question. Even if it's compromised, the moment you and you don't know about it, the moment you rotate the secret, it's no longer valid. The other thing as well, can it be revoked? For example, if we know we're compromised, or we just want to rotate it, does it invalidate some sort of secrets that we produced out of this? And this happens a lot with HMACs, which we'll see in the JWTs in a bit. When we create an HMAC, we have a secret key as well, and all those signatures are linked to that key. The moment we rotate the key, that means that that all those signatures are invalidated as well, and that's what Azure Storage uses, for example. Another spot to bug. This is derived from an example which we found in Azure, where we create passwords. And looking at the source code, I would ask, can you spot a security bug with the same delay in Teams? I may talk a little bit through it. It's not the fact that the length is only 8, because we can change the length to as much what we want. The biggest problem here is that we use this function called random, and random in .NET is not cryptographically secure. Now, some of you may have heard that randomness is a big deal in security, especially when creating keys or when creating passwords. And people might ask, why is randomness so important? In .NET, and this is a program you can download from my GitHub. In .NET, when the random function is called without a seed, it uses a system default. And in the classic .NET framework, that's time dependent. In .NET Core, there's a PRNG, a pseudo-random number generator with that. The seed, or what the random function does, it gives you a random order of numbers, and the seed controls what your initial number is. So the same seed means the same values. And in fact, and this is a program that a colleague and friend, Rohit of mine wrote, and I borrowed his source code. If you generate 10,000 passwords in a classic .NET with a random function, you can see on the snippet there, you actually get 2 passwords, 2 or 3 if you're lucky. And it doesn't mean it, or it doesn't matter if you're generating an 8-character password or 16-character password. When you think you created 10,000 passwords, you really created 10. So when you're building a service that generates a lot of secrets for different users or a lot of secrets for different resources, you might actually have quite some collisions in there. And if you're not using .NET Core, in .NET Core you get some 9,997 out of 10,000. But if you're using the classical .NET framework, you might actually have quite some collisions, and your machines or your resources or your users might end up with the same password for quite a bit, and quite a significant number as well. So you can download this. It has both the classical .NET program in there as well as the .NET Core program in there, and play around with it. So if random is such a bad thing, when you're making a secret, when using passwords or symmetric keys, make sure it's cryptographically random. In .NET, we use this. We do this using the RNG crypto service provider, and which is a little bit of code snippet there. Node.js and C, you can do it in different ways. Initially, these slides were made for a very developer audience. In Node.js, there's the crypto module, which is cryptographically secure, and in C, srand and rand isn't. And for that, we would need to use the Mersenne twister. Within Microsoft as well, we get a lot of questions saying we're not using this for security measures. We're just using this to generate a random number. Is it that important? That sort of depends on you. If you need true randomness, whether you're creating winning numbers or unique URLs, you might want to increase the randomness there. Moving on to making JOTs, many identity providers such as Active Directory do some of the heavy lifting, and they return something called a JWT, and people pronounce it as a JOT, which is a JSON Web Token, really. It looks encrypted. You can see one there. But really, it's an URL encoded, base 64 encoded, signed JSON message. URL encoded means it won't have any equal signs in there, so it makes it safe to use in a URL as well. All the equal sign padding is sort of cut away in case you ever need to construct one. And other than that, they're just base 64 and signed. And instead, they're not typically encrypted; they're signed. And if you would decode the JOT, what we have there, you would actually see that there are 2 JSON snippets and a signature at the end of it. The first one is something we call the header. We can say that there's a type in there, and it's a JOT, it's a JSON Web Token, and that there's a certain algorithm being used, the HS256. The payload itself, the subject says that authentication is cool. We all agree on that, and that it will expire at some day. And I think this date actually says the moment this webinar started, this one expired. What are the problems with that? These HS256 or other key sizes are actually symmetric keys. They can be cracked offline as well. In fact, the JOT that we saw earlier is just signed with the key Microsoft. Now that's hard to, let me go back to slide. That's hard to just see from this snippet. When we see this JOT in source code or in a log file somewhere, we may say, hey, it's signed, and move on. But if you analyze the header, you can actually find out that this is a symmetric key. Most of the symmetric keys we use are text-based strings anyhow. So an attacker may look at your JOT, take it offline, crack it offline, and even if your JOT expired or not, as long as you don't as long as you don't rotate a secret, in this case Microsoft, you might actually guess the key. When you have the signature, then everything in that payload becomes moot. It sort of becomes the same authenticity of the note that your mom would sign. The moment you know that there's a fake signature, you cannot trust the entire document anymore. For that, we should opt for asymmetric keys, RSA keys. You have a public key pair and a private key pair. You can have it's easier for key distribution. You can have multiple keys to facilitate this key rotation. You can say these secrets or these JOTs are signed with this public key, and here's another public key for the future, and you can use multiple keys at once to make the rotation a lot easier. If you ever receive a JOT, and even people say this is coming from a system and you can trust it, you should always validate the presence of a signature, and you should always validate the signature, because otherwise, as I said, it turns the entire payload basically untrusted. Moving to the final part, then we found out how to talk to the right endpoints. We know how to create or get our secrets securely from the right places, or create them and leverage a lot of the platform information what we have. How do we handle them, and how do we store them now? One of the big things we see is that secrets end up in log files. So one thing we would say there is be very mindful of what you log. And part of that is usually in penetration tests, the pattern which we recognize is that when something goes wrong, when an exception, when we didn't really anticipate an exception, we throw everything to telemetry, or we throw everything to a log file, and we sort of say, this is the web request, and this is the stack trace, and this is our entire context of whatever went wrong. The downside with that is that web requests, usually, if you have authentication, would either contain authorization tokens, such as bear tokens or what AED gives you, or cookies in a normal web application. When you dump an entire web request, that information is in there. Tokens expire after a certain time. I know that. Cookies can be long-lived. So if this ends up in log files, you might actually leak a lot more than what you know. People who have access to log files could see these things, and then would be able to access your service. This doesn't just happen in source code, in the code where you do something, where you do all the business logic. This could also happen in .NET, for example, in these middlewares in a .NET application. For example, action filter attributes is a typical attribute where you can say on every request, do this thing, especially during debugging, which is often a flag. You could say on debugging, log every request because I want to see afterwards what's happening. And that is bad. So make sure you check your source code as well as all the middlewares inside .NET applications. When we create a stack trace, whether we put them in a log file or we display them to the user, they could have sensitive information as well. So make sure you scrub them before you log and never display them to the user. For, as I said, stack traces could have information you don't really want to leak there. And also, don't leak secrets that you're using, saying, oh, we got this access token from Key Vault, or this is the connection string. We got it successfully. Here's proof that the connection string is there. Because someday, some partner team will come to you and need access to your log file, read-only access for debugging purposes. And someone on your team will say, it's read-only access. It's not a big deal. We can grant this user access. Also, for telemetry data, don't store anything in there, obviously. What we can do about it is filter them out early. For example, if you detect what type of secrets you have, you can filter for certain patterns. The JOT, which we saw earlier, which I put there as well, I highlighted some of the patterns that make it easy. You can see that it's a string dot another string dot another string. Now the first two strings are actually JSON bodies, so we can easily detect them and determine whether they're JOTs. If they are, we should eradicate them as soon as possible. If we don't have them in memory anymore, even if we end up dumping an entire web request for some debugging purposes, our token will be removed in there. So that's a handy thing. And then finally, I wanna talk about when we store or handle secrets. If you need to deal with them temporarily, then they need to be in memory, preferably in bytes, because a secure string in .NET is no longer recommended. Secure string works very well on Windows. It doesn't work so well on Linux and OS X machines. But for that, we basically tell everybody to use bytes instead of a secure string. One of the issues of secure string as well is that it's your data probably came in as a string, and you're probably passing it on as a string as well. So it's somewhere in memory, but keep it as small as possible. If you're caching any data, a lot of people might say when we talk to Key Vault has a rating limit, which is true. I believe it allows 2,000 requests every 10 seconds. Pretty decent rating limit. If you would hit that rate limit, you can cache them locally in memory cache, but make sure you clean up your cache when it's no longer needed. If you keep secrets, API keys, and passwords around in memory, that'll always be someone is always bound to find them. What you don't have in memory, people can't find. If you need to persist them locally, if you need to store them somewhere, we try to say I'll jump to the cloud thing first. If you're in the cloud, store your secrets in approved secret stores. Within Azure, we try to push for Azure Key Vault as much as possible. As I said, you can cache it locally if rate limiting is an issue, but otherwise dump your secrets there. It's easier, they're all there, they're audited, and you know that's the keys of the kingdom. There's only one area you need to monitor very closely rather than them being scattered all over the place. Jumping back to storing them locally, you might not always have access to the cloud. If you need to store them locally, see if there are any provided security mechanisms that you could use. For example, Windows has a thing called DP API, which is a data protection API. It will encrypt a secret to that machine and that user session. So I would encrypt something and only my user session on my Windows machine would be able to see it and no one else. In Linux, we don't have something like that. Now, there are programs that come close. OS X has a keychain. Both GNOME and KDE have a sort of local key store, if you like, but there's no native product that works over all the different distributions. So for that, we would tell people to fall back to restricted file permissions, but you do have to keep in mind that root can read any file in there. So if you do put a secret somewhere in a file, make sure that you know who could get root, both processes as well as people on that machine. So with that, to recap everything, as I said, authentication authorization is important. With that, if you stick to these 3 rules, you're probably quite well off. Make sure that all the endpoints that you talk to, that you trust them and that you can validate them. So don't talk to endpoints you don't fully trust. When you create signatures, analyze the characteristics, whether humans need to know them, or whether they can be expired on demand or whatnot. When you create them, always use strong randomness. You want your secrets to be unguessable, and only strong randomness can do that. When you get any data, such as JWTs, such as JSON Web Tokens, verify the signature of it. If it's data you don't trust and you know the partner team, see if there's some way that they can sign it, because if you can validate the signature, you know that the data you're working with can be trusted and no one tampered it in between. And when you store secrets, when you store secret data, use existing platforms that are there. Eradicate the secret as soon as possible. If you need to authenticate something and you don't need it anymore, remove it from cache, remove it from memory as much as possible. And when you do any logging, telemetry, or debugging, make sure to that none of these secrets end up in there. And with that, I would like to thank you. And we can go to questions now. I think, Fallon, it's back to you.
Thank you, Michael, for sharing this helpful information. Although Apurav and Molly has done a phenomenal job on replying to all the questions, I think Ryan may have something for you.
Yeah, so Michael, you covered several different types of bugs. What would you say is the one you most commonly run into?
Unfortunately, we still see a lot of secrets being passed around insecurely. Obviously, security bugs. We do pen tests in multiple areas. So if we look at networking, we see a lot of networking issues and there, but a lot of secrets end up being handled poorly. That is either that they're being logged and they end up in a log file, and service teams are not aware who's all looking at the log file, or they are in source code that which is usually that initial bootstrapping secret. We need a cert to talk to a key vault to download all the rest. So we still occasionally see secrets in source code.
Okay, got it. Great. And of all those bugs you talked about, and in a related question here, what are the most severe? What's the most severe type that you run into?
Obviously of all the bugs we fixed, the severe ones they're usually a combination of something. So, for example, a typical web security vulnerability called SSRF, server-side request forgery, could just be one part of a chain. It could be this just a possibility to send a message outside to an attacker server. If you chain these up with let's say local file reading capabilities, you can actually create an exploit chain that reads local files and exfiltrate them outside. And this is sometimes possible with, and I'll call out Molly here for a second. She's done a ton of research on XXE vulnerabilities, which is purely by ingesting XML data. You can read, if you do it wrongly, you can read local files and read external files, which pretty much means you can read local files, exfiltrate data, and read them outside. If this is running in some sort of elevated privileges, especially root and whatnot, you can read any file on the file system and send them to an attacker server. And those are the bad ones that are hard to find. It's not easy detecting all of this just in static analysis. Yeah, it's hard to find these exploit chains. Those are the big ones, the chains. So somehow.
Cool. There's some questions coming in. Looks like Molly's tackling one, so I'll leave that one to her. There's another one asking, is there a pen testing tool available from Microsoft?
There are, we should probably take that offline because I don't know where they all are. There are a ton of tools that Microsoft use that are open sourced. A few that come to mind that I know of by heart, obviously, because I deal with them every day. One of our sister teams created CredScan, and as the name implies, it scans for credentials in source code. It does a lot of pattern matching, and our team, when we do a pen test, we feed back into it. We have humans look at source code as well. And surprisingly, developers can sometimes get very creative on hiding secrets. Instead of just saying string password is Azure 123, they actually convert it into a byte array already and have each character separately. Secure from a memory handling point of view, but someone who reads the source code can still see that. So every time we see that, we feed it back to CredScan. CredScan is a big one. BinSkim is a big one as well. Those are very static analysis based. It looks at source code and looks at the problem there. There are a few more that I personally like a lot. One is called Wrestler to do API fuzzing, but that's something we should probably take offline. I don't think you want me to just list out a bunch of tools that come to mind. I'm sure we have a list somewhere that I can share afterwards. So to say, these are the public Microsoft pen testing tools, and we're creating new ones that we want to open source as well.
Sounds good. The next question is the sorry, what is the best method to store the password when we are connecting to Azure via PowerShell?
If you're running PowerShell on, so storing the password, do you have more information on that? You mean locally or?
The example is, for example, connect Azure command, the cmdlet. Well,
Got it.
Yeah.
I personally, I don't use the PowerShell commands that much. I know that the Azure CLI uses a file, and that's purely because I spend a lot of time in Linux. It's in a certain path. In PowerShell, I believe they try to use when you log in, it stores the credentials locally, and I think it falls back to DP API, to the data protection API in Windows. Otherwise, it's a file if you're using PowerShell on Linux, I believe.
Okay.
Not 100% sure though.
What about get automation variable? Is this a good way to storing a secret outside of the source code for Azure automation?
It would be if you know that, or if you know who has access to your environment variables. So, for example, what a lot of people do initially is when they create, let's say, an Azure app service, they put all their secrets in environment variables, their connection strings and whatnot. It's good because it takes it out of the source code. There's no password visible in source code. It does mean that whoever has a certain permission on your resources will be able to see those secrets. Now, I don't think that reader permissions have access to environment variables anymore, but there are more or if you know all the processes and users that can see your environment variables, and you trust those, that should be okay. But at least it's usually bigger than you think. Every time we do a pen test and we get some sort of memory access or shell execution, the first thing we look at is environment variables, because 9 out of 10, somewhere in there, there's a connection string there for some program to pick up. So it's not bad if you trust everybody who can read it and if you know them.
Great. Well, thanks again, Michael, and thank you to Apoorv Dayal and Molly Watson for your help on answering the rest of the questions. And so just a quick reminder for that the best way to ensure that you don't miss any future webinars or major announcements, please visit our landing page at aka.ms/security community. And while you're there, you'll see that you'll be able to find easy ways to navigate and find resources as well as the learning content relevant to our security products and to your needs. A good start would be browsing our bite-sized product videos, ninja trainings, as well as the recordings of the past webinars, and the GitHub communities and more. So I would like to close this webinar by thanking all of you for being part of our community and for joining us on these webinars. We hope to see you next time. Goodbye.
Thank you, Valan.